Hello, my name is Dalal Paulette. I'm a postdoctoral researcher with John Hutchinson on the Dawn Dinos project at the Royal Veterinary College. And in this project, we're interested in learning more about how the extinct crocodile-line archosaur named Batrachotomus would have moved. It's an animal that lived about 240 million years ago in the Middle Triassic. And it has some features that we think of when we think of modern day crocodiles, such as a large head, a long, massive tail, but then it has other features that we don't see in its modern day relatives. It has these long, erect, adducted limbs that are more similar to, say, the pose of a modern mammal. And so the question is whether it would have moved more like a modern day crocodilian, or would it have moved more like a modern day mammal? Now we have some trackways that we can assign to Batrachotomus, or at least to a close relative. These belong to the Ichnotaxa Brachychirotherium and Isochirotherium. And we can get some information from these trackways. For example, we can get the stride length using an empirical equation. We can deduce its estimated speed if we have some measure of the hip height. But apart from that, we don't get too much information about the gait. Now, one other parameter we do have is the track phase. So this is the distance between pes and ipsilateral manus divided by the stride length, and that's a measure of track phase. So in this example, the track phase would be fairly close to zero, since the manus is pretty close to the pes. And from these trackways and from the track phase, you can make some assumptions about the gait, but not too much, because many different gaits can give very similar track phase. So what we wanted to see is whether predictive simulation could come up with the same track phase that we observe here. And if it does, then we can make some inferences about the gait of this extinct animal. So we use a very simple model. All it is basically just one rigid link with 4 legs. And these legs are completely massless, and all that they can do is push. Now, the advantage of such a simple model is that we can use trajectory optimization. We can do a ton of different guesses, and we can find an optimal solution that doesn't pre-specify contact sequence. So we can have basically any symmetrical contact sequence the optimizer chooses. And we can look at all the different guesses or all the different solutions from the different guesses and choose the best one. So this is sort of a pseudo-global optimization procedure. And so in our group, we've done a volumetric model of Batrachotomus, and so we can have some estimate of the mass and the mass distribution. We can pose the model in some sort of lifelike configuration and get some measurements of the hind limb length, the forelimb length, and the pitch moment of inertia, as well as the center of mass position. And those are the only morphological inputs we need, as well as the distance between a glenoid and acetabulum. And then from the trackways, we get some measure of stride length and speed, as I discussed before. And so those are the only inputs we need to the model, and then everything else comes for free. And the main thing we're interested in is track phase. And so we're going to compare the outputs of the model for track phase to the actual trackways. But first we want to see if the model is actually any good. So we used data for dogs, or morphological input for dogs as input, and we tested the track phase as output. And what we find is that it does follow pretty closely to the empirical data. So this line is the average value for Belgian Malinois dogs, within some sort of natural variation, which is the colored area here and here. And we do see this behavior of track phase decreasing as a function of speed, and then this jump when it goes from a walk to a trot, and then decreasing again, which qualitatively matches the empirical data and is within natural variation. But there is some discrepancy. And there's the sensitivity of force rate penalty, which I didn't talk about yet. Basically, the cost is a combination of work from the legs as well as a penalty for rapidly changing force. And this parameter C modulates whether this force rate penalty is large or small. And at a relatively large value, we get the best fit for dogs, a relatively large value of the force rate penalty. Now for Batrachotomus, we also see the sensitivity of force rate penalty. So we have a very large force rate penalty up here, decreasing, and then the lowest value seems to be the best fit to the empirical trackway data, in the sense that the track phase is fairly constant with speed, and that's the behavior that we see as well with the Batrachotomus simulations. However, it's off by a constant factor, so that is something that we need to resolve in future. But if we just take the qualitative agreement with empirical data as a good sign, then we can look a bit more closely at the gait. And the gait is a little bit unusual that's predicted by the model. At slow speeds, it predicts this walking trot, as you can see by the ground reaction forces. And it might be better to just show a video here. So this is the simulation at a slow speed. Oh, let's just go back a bit. It's a walking trot, as you can see. Then at high speeds, it transitions to what we would consider a tolt, where it vaults in the hind legs and then pushes off in the forelegs. And this is a behavior that we see in almost no modern animals. The one exception would be the Icelandic horse, which does use a tolt pattern. And so it's a very unusual gait even for mammals, and it's unheard of in modern day archosaurs. So the predictive simulation predicts something that is quite unusual, but it's an example of how predictive simulation can surprise us, and that we can't always assume that modern extant relatives give some idea or give a very close idea of how extinct animals would have moved, particularly when their morphology is so different from modern animals. In the future, we'd like to resolve this discrepancy between the predicted track phase and the empirical track phase. And one way we'll do that is by adding masses to these legs, as we think that that really affects the phase relationship of the limbs. And another thing that we'll do is do a deeper dive in the literature and see if there's any data on trackways with at a lower presumed speed, and whether the track phase actually increases with lower speed, which would match this sort of elbow behavior of as we transition from a walk to a tolt. So I hope you can take some time to look more closely at the poster. You can follow these links to see some more videos, and I look forward to interacting with you at Adaptive Motion of Animals and Machines.